In this session, we'll try and understand the torque speed characteristics of an induction motor. Understanding the torque speed characteristics of any motor is important so that we can decide for the maximum torque or the starting torque of the motor uh, with respect to the speed of the motor. Uh, every type of motor, be it a DC series motor, DC shunt motor, synchronous motors, or induction motors, they have their own torque speed characteristics, and depending upon their torque speed characteristics, we can try and we can decide for where they are more suitable, which application they are more suited for. In some applications, we need a very high starting torque. In other applications, we need a low starting torque. So accordingly, we can decide for which motor is best suited for which application. Now, to derive the torque speed characteristics of induction motor, we will be deriving the Thevenin's equivalent of the equivalent circuit of the induction motor. This is the equivalent circuit of our induction motor. We already know, we have already derived this. We will be deriving its Thevenin's equivalent so that we can derive an equation that relates the torque with the speed of the induction motor. In order to derive the Thevenin's equivalent, we need to derive its Thevenin's voltage and its Thevenin's impedance. So the first step, deriving the Thevenin's voltage, we open the rotor end. We can calculate the Thevenin's voltage using this circuit after opening the rotor side, and also assuming that RC is negligible as compared to the magnetizing reactance. Uh, so using this circuit, we can calculate VTH as uh, from the voltage divider rule, simply as using this equation as V phase XM divided by under root of R1 square plus X1 plus X1 M square. We also know that the magnetizing inductance or the magnetizing reactance is pretty, it is much larger as compared to the leakage flux reactance of the stator. That's Xm is much greater than X1, as well as Xm is much larger than R1. So we can neglect those values of R1, and we can approximately say that Thevenin's voltage here is V phase divided by Xm divided by X1 plus Xm. Now the next step will be deriving the Thevenin's uh, impedance. For that we need to remove the voltage source. The voltage source has been removed by shorting it. Simply looking at it from this side, R1 plus JX1 is in parallel with XM, and again assuming that Xm is much larger than X1 and Xm plus X1 is much larger than R1, we'll find out the values of RTH and XTH. Now we are finding the Thevenin's impedance here, so we have to find out its resistive part as well as its reactive part. Now since we have obtained RTH and XTH, we have also obtained VTH. Now using Thevenin's using the known knowledge of Thevenin's equivalent circuit, we can place the Thevenin's resistance, Thevenin's impedance in series with the load circuit. That was actually the rotor side. The rotor side comprised of its own reactance and its own resistance, and replacing the voltage by the Thevenin's voltage equivalent. Now solving this circuit for the air gap power, we can solve this using these equations. We know that the current flowing in this circuit, I2 I2 is actually the current flowing in the rotor circuit. We can now easily calculate it as VTH divided by RTH plus JXTH plus JX2 plus R2 by S. And we know the air gap power is nothing but thrice I2 square divided by into R2 by S. So replacing the value of putting the value of I2 that we have calculated from the Thevenin's equivalent circuit, we'll get PAG, the air gap power, equal to thrice VT square R2 by S divided by R2 RT plus R2 by S plus XT plus X2 whole square. We already know that the induced power that we have derived in the last induced torque that we derived in the last session is equal to air gap power divided by the synchronous speed of the induction motor. Replacing the substituting the value of air gap power, we will obtain this equation. So this is our equation now that relates our torque with the slip of the induction motor. Torque induced versus slip. We have not calculated, we have not obtained the equation of torque versus speed directly. We have obtained the equation of torque with respect to slip of the induction motor. Keeping in mind that omega synchronous speed of the induction motor is constant, it does not change. We are not plotting versus the synchronous speed of the induction motor. We need to obtain a plot of torque with respect to the rotor speed of the induction motor. Since we have obtained the equation of torque with respect to slip of induction motor, we already know there is a relationship between slip and induction motor, slip and rotor speed. So using that knowledge, we can obtain the torque speed characteristics of the induction motor. That's the torque versus the speed of induction motor. Slip, as we understand, is nothing but ns minus nr divided by ns. Slip is ns minus nr divided by ns. If nr is 0, slip will be 1. If nr is equal to ns, slip will be 0. So as the rotor speed increases from 0 to ns, this is rotor is increasing from 0 to the synchronous speed of the induction motor. Slip gets reduced from 1 to 0. So this is means slip is 1 here and slip is 0 here. Now once we plot the torque versus the slip of the induction motor, that will actually be also the torque versus speed of the induction motor, but only the reverse of that. So using this equation now, 3VTH square R2 by S divided by omega this whole, using this whole equation that we have obtained here, we will plot torque versus slip of the induction motor. So once we do that, we'll see that the torque versus slip of the induction motor varies in this fashion. As S increases from 0 to 1, torque will change in this fashion. So as slip is varying from 0 to 1, we can see torque varies in this fashion. We can also show it like this. This is our torque equation that we obtain with respect to S. So take different values of S. We have S in the numerator, we have S in the denominator. So as S increases, this is S. It can take any value from 0 to 1, that means from 0 to 100%. So torque will increase initially linearly with respect to synchronous with respect to slip. Then it will reach a peak and then it will vary inversely. So at s equal to 1, our torque will not be equal to 0. There will be a finite value of torque at s equal to 1. At s equal to 0, the induced torque will be 0. So just flipping this graph. Once we flip this graph, this means here S is 0 and S is 1. S is equal to 1 simply implies that NR is 0 at this point, and S equal to 0 simply implies that NR is equal to NS. So all this graph also gives us the variation of torque with respect to the speed, with respect to the rotor speed of the induction motor. So as speed of the induction motor increases from 0 to synchronous speed, we can see the torque varies in this fashion. So this is actually the torque speed characteristics of the induction motor. Now what happens beyond if NR becomes greater than NS, that is greater than the synchronous speed, slip will obviously take a negative value. Uh, that's actually corresponds to the generating operation of the induction machine. That means if our rotor speed becomes greater than the synchronous speed, instead of uh, delivering power from the source to the load, it will be the load that will be now delivering power back to the source. So our induction machine will be operating as a generator. And if we for this portion of the graph, NR is less than 0, that means simply our induction motor is not rotating at this time. That means it corresponds to the braking region of the induction machine. Uh, so there are three regions of torque speed characteristics. One region where it corresponds to rotor speed from 0 to synchronous speed. That's the motoring operation that we are actually dealing with right now. Another region is the generating operation where rotor speed becomes greater than the synchronous speed. Instead of receiving power, the load becomes the source of the energy. It will supply back the power to the motor. This happens in case of regenerative braking, as in case of once regenerative braking can be applied in case of electrical vehicles or traction systems, where we want to, in case of we have to stop our vehicle. Instead of mechanically doing that, we will try to increase the speed of rotation. Uh, what actually happens is that the motor now becomes a source of energy, becomes a generator, and instead of uh, the power getting lost, that happens in case of mechanical braking. Here, the uh, power will flow back into the system, and we can have, say, for example, a battery there that will become a source of energy. The concept of regenerative braking will be discussed in detail in another lecture. And S for all speeds corresponding to NR less than 0, that actually means slip is greater than 1. We have the braking region here. Our rotor is simply is not rotating. So we have three modes of operation: the braking or the plugging region, the motoring mode of operation, and the generating mode of operation. We saw the variation of torque with respect to slip as slip increased from 0 to 1. Now, since we know how slip varies with respect to the rotor speed, we can say the torque is varying with respect to rotor speed in this fashion. So, this is about the torque speed characteristics of the induction motor. In the next session, we will try to see how we can calculate the motor parameters, and also we'll look into different speed control techniques of induction motor.